Welcome back. So in this talk, I'll discuss about Ensemble deep learning for Alzheimer disease diagnosis. So essentially, I'll discuss deep learning, Ensemble deep learning, and their applications for Alzheimer disease. So as I started with, thanks to my students, my team at IIT Indore, some of them already left to another institutions. Thanks to all of them for their contributions. So now I'll start with the basics, that what is Alzheimer disease? Alzheimer disease is a neurological disorder disease. So, and it has been named after German doctor Alzheimer, who was the first to diagnose Alzheimer disease in 1906. And it is characterized by the accumulation of amyloid plaques and neurofibrillary tangles in the brain. So mostly this disease comes of age 65 and above, and it causes cell damage and death in critical brain areas, impacting memory and cognitive function. According to the report in 2018, around 50 million people were affected by this disease, and it is expected to triple. That is 150 million people to be affected by 2050, as per this report. So now, if we look at the symptoms, Alzheimer's disease manifests through various symptoms affecting cognitive functions. Recognize these functions signs early is crucial for timely intervention and management. So these are a few symptoms as I can see in this slide. The first is that challenges in planning or solving problems. Another is confusing day from night, inappropriate use of words, mood changes, memory loss, gradual loss of ability to perform normal tasks, loss of vision and coordination, inability to recognize and use familiar objects. So if we see here, we have two different kind of brains. One is healthy brain and another is Alzheimer brain. So in the first figure, that is figure A, we can see this image. It illustrates the tangible impact of Alzheimer disease on the brain. On the left side, left side is the healthy brain, and the right hand side you can see Alzheimer brain. So you can see a significant difference between these two different brains. So it essentially, right hand side, it reveal a noticeable size disparity between affected and healthy brains. So the atrophy seen in the Alzheimer affected here, uh, it underscored the structural changes associated with the disease, and it emphasized the importance of early detection and intervention and preserving cognitive health. And if I look at the right-hand side figure, so we have the Alzheimer cells and healthy cells. So a clear visualization is presented between Alzheimer affected cells and their healthy counterparts. So the distinctive feature highlights the structural difference, providing a visual insight into the impact of the disease on cellular health. So this visual representation is a valuable tool for understanding the cellular changes associated with the Alzheimer's disease. So deep learning and Alzheimer disease detections, essentially neuroimaging techniques are crucial in the timely detection, a diagnostic assessment, and therapeutic intervention of Alzheimer's disease. And neuroimage analysis traditionally involve human experts such as radiology and clinicians. However, for sheer volume of neuroimages poses challenges as the process is time consuming and vulnerable to human disease. So essentially, doctors and researchers harness ensemble and deep learning techniques to automatically discover useful features and interpret the neuroimages to enhance efficiency. And recently, deep learning has rapidly become a preferred tool for neuroimage analysis to detect Alzheimer's disease. So I would discuss a few steps that how research impact the society. First is the early detection and intervention. So our deep learning model facilitates early detection of Alzheimer's, which is crucial for timely intervention and enhancing healthcare accessibility. The development of an accurate Alzheimer detection model contribute to making diagnostic tools more widely accessible, facilitating timely medical attention and support for affecting individuals. Advancing research and understanding by leveraging deep learning, we contribute to a deeper understanding of Alzheimer, advancing both clinical applications and broader neurogenerative research. So this is essentially the first comprehensive review on ensemble deep learning. So this is the first attempt in the uh, literature to write a comprehensive review on ensemble deep learning. So here we cover the theoretical aspect and different ensemble strategies and several applications, including healthcare, speech, image classification, forecasting, and several other applications. And we have given our recommendations for future work. So this work was published in just 1 year ago, and it has been cited more than 650 citations in just 1 year. So now this is another review paper on let me. This is another review paper on RVFL network. So you can see that, let me give a pause just for a minute. Yeah, sorry. So I was discussing about this one review paper on ensemble deep learning. As I mentioned that this is the first attempt in the direction of ensemble deep learning. So, and essentially this review paper reviews the state of art deep learning and ensemble deep learning models. And it essentially serves as an extensive summary for the researchers. And the ensemble models are broadly categorized into, you can see, bagging, boosting, stacking, negative correlation, explicit, implicit, homogeneous, heterogeneous, and the decision fusion strategies based ensemble models. And we can see several different applications. And finally, we conclude this paper with some potential future directions with our recommendations. Now, this is also very interesting that this is also the first review in the literature on RVFL. RVFL was introduced in 1994, and after 29 years. So this is the first review paper and published recently in Applied Soft Computing. So RVFL model has several characteristics such as fast training speed, direct link, simple architecture, and it has universal approximation capability that make it a viable randomized neural network. And this review paper present essentially, as I mentioned, the first comprehensive review on the evolution of RVFL model. It can serve as an extensive summary for the beginners as well as the practitioner. So here we discuss the shallow RVFL, ensemble RVFL, deep RVFL, and ensemble deep RVFL models. And the variations, improvements, and applications of RVFL models are discussed in detail. Further, we discuss the different hyperparameter optimization techniques followed in the literature to improve the generalization performance of the RVFL model. And finally, we present potential future directions, opportunities that can inspire the researchers to improve the RVFL architecture and learning algorithms further. So this is the basics artificial neural network. So there are several types of neural network architectures depending on structures, internal functioning, and applications. Generally, an artificial neural network training phase is an iterative process in which all the parameters are adjusted using the back propagation approach. And there are several limitations of backpropagation approach, that it has slow convergence, it may fail to attend global minima, and it is also sensitive to learning rates. So to move ahead, this is the randomized neural network. I just show RVFL review paper. So I'm focused there only. So there is another family of neural network called randomized neural network. And randomized neural network with closed form solution avoid the shortcoming of conventional backpropagation based training neural networks. And randomized neural network has simple architecture, strong mathematical foundations, and effective data modeling capacity. So in randomized neural network like random vector functional link and extreme learning machine, some of the parameters are fixed while training, either in stochastic or deterministic fashion, and the rest parameters are optimized via closed form or iterative methods. Some of the advantages of randomized based models that it has less computational cost, fast training speed, and better performance. So I'll start with the formulation of random vector functional link. So random vector functional link is essentially is a randomized version of a single hidden layer feed forward neural network. So we can see here. So essentially, we can see we have the three layers. If we talk about a single hidden network called RVFL network. So one is input layer, another is hidden layer, and the last is output layer. And all three layers consist of neurons connected via weights. So to avoid the implementation of the back propagation algorithm, the weights from the input layer to hidden layer are generated randomly from a given domain and kept fixed during the training process. Only the output weights are analytically computed by the least square method or pseudo inverse method. So in RVFL, original features are given as input to output layer via direct links, and the direct links are usually improve the generalization performance of RVFL. This is as per the literature. And this is what the architecture of the and optimization problem of RVFL with L hidden node. It can be represented here. We can see we have minimized C by 2 norm of H beta minus Y whole square plus half norm of beta square. So, and where beta is an output weight matrix and H is the concatenated matrix of input data and output from the enhancement nodes. And here Y is the target matrix and H and beta can be shown here. H is H1 and H2. And the solution we can compete with the equation 2. Here C is a parameter and I is a identity matrix of appropriate dimension. So now moving ahead, let us discuss the another variant that is the deep variant of RVFL network that is called a deep random vector functional link. So Sugandhan team and myself, we developed this idea in 2021, published in Pattern Recognition. So the deep random vector functional link is an extension of the shallow RVFL network in the context of representation learning or deep learning. So this network is characterized by a stacked hierarchy of hidden layers, as we can see in this figure. And the input to each layer in the stack is the output of the preceding layer, wherein each layer builds an internal representation of the input data. Although the stacked hierarchical organization of hidden layers in deep RVFL network allow generally flexibility in the size, both in depth and width. Uh, for the sake of simplicity, here let us consider a stack of L layers. You can see up to and there's L hidden layers, each of which contain the same number of hidden nodes, like N. So here for easy notations, we just omit the bias term in the formula. So we just write the output of the first hidden layer in equation 3, that is H equal to G, H1 equal to phi of XW. And the output of higher hidden layers, it can be represented in equation 4, that is Hi equal to phi of Hi minus 1 WR, where phi is a non-constant activation function and W belongs to R with size D cross HL. And they are the random weight matrices. And finally, one can find out the output layer weights with K hidden layer features with the H star in equation 5. So the output parameter beta can be calculated similar to the standard RVFL using this H star. And if you look at the ensemble deep RVFL variant, so the only thing that we have incorporated the strategy of ensemble learning. Ensemble learning approach incorporated in the deep RVFL network so that multiple diverse and accurate base models can be generated. So, so this ensemble deep RVFL essentially serve three purposes. So one is instead of using only the higher level representation, that is feature extracted from the final hidden layer of the data, as we see in conventional deep learning for classification, this ensemble deep RVFL employ rich intermediate features also for final decision. And second is that ensemble is obtained by training a single deep RVFL network once with a training cost slightly higher than that of a single deep RVFL. But it is cheaper than the training several independent model of deep RVFL. And finally, like a deep RVFL, ensemble deep RVFL model framework is generic and any RVFL variant can be used for this. This is the advantage of using ensemble deep RVFL. So in the last 2 years, a lot of work have been done by the researchers by using this ensemble deep RVFL variants. So this course is also publicly available on the GitHub repository. So one can see and use it directly. So this is a simple architecture uh, simple architectures of Ensemble deep RVFL, and output of the first layer can be represented as like H1 phi of XW1, similar to deep RVFL, and output of the higher hidden layer can be represented in equation 7. And final output can be calculated similar to extended RVFL model. Now, I'm moving forward to discuss some recent contributions, especially uh, especially this ensemble deep learning uh, RVFL variants, and introducing learning using privilege information and applications to Alzheimer disease. So this is the idea of this work, and this is called Ensemble Deep RVFL Plus. So, and in this work, we have developed two variant. One is Deep RVFL Plus, and another is Ensemble Deep RVFL Plus. So, novel deep RVFL network using privilege information is proposed. And another is that we have Ensemble deep RVFL using privilege information called EDRVFL Plus is also proposed. The ensemble model is trained in a manner that higher layers of model that utilize the original information as well as the non-linearly projected features from the lower layers to train the network. So if you look at let's first discuss its architecture, and then we can come to the mathematical formulation. So this is essentially the graphical representation of deep RVFL plus. So the architecture, we can see from this architecture that this deep RVFL plus, it consists of two components. One is left side a normal component, and the right hand side we have the privilege component, or we can say normal information and privilege information. So the left side, that is normal information, is processed through L number of uh, hidden layers, with each layer receiving the input from the previous layer. And here we can see that we have followed a rectangular structure where the number of nodes in each hidden layer is fixed, that is n, and the weights and biases given by here WI, BI, that is W1, B1, W2, B2, and so on. So they are generated randomly and we kept fixed. So, and we have the right hand side privilege information. So privilege information is also generated by a layer architecture wherein we input the original features. However, the privilege information uh, or privilege component of the given architecture uses separate set of weights and biases. So we can denote W tilde and B tilde I. So, and they are also generated randomly and kept fixed. And we use different activation functions in the privileged component. So similar to normal component, we fix the rectangular component with the n number of hidden nodes in each hidden layer of the L layer architecture. And the output of the first privilege layer, we can see here in equation 16, in equation 8, that is H1 equal to GXW, and for higher layer, we have HI equal to G, HI minus 1 WI, where W1 and so on WI. So, and G is activation functions. And we can concatenate this input data matrix to the output layer and represent it as D. And the output of the first privilege hidden layer can be represented in the H tilde are 1, and we have a different activation function f, that is f of x w tilde by 1. So, and similarly, we have the higher layers, and we have the concatenated matrix for the privilege one. And finally, we have the output weights of deep RVFL plus are optimized by solving the optimization problem of 14, that we minimize half norm of beta square plus sigma by 2 norm of beta tilde square plus c summation this xi I beta tilde comma f h tilde xi subject to the equality constraints, and optimal weights can be calculated like in equation 50. Okay. Now, to move ahead, we need also to discuss the ensemble deep RVFL plus. So I think first we can discuss the architecture of ensemble deep RVFL plus, and then we can discuss the mathematical formulation. So what we are doing here. So here the concatenation of all the projections of hidden layers in a single matrix in deep RVFL plus exaggerated the complexity of the algorithm. So to overcome that issue, here we developed Ensemble Deep RVFL Plus, that is EDRVFL Plus. It utilized the intermediate features, unlike conventional multi-layer architecture, which results in improved generalization. So this is we can see that in a similar to deep RVFL plus, we also have two components, that is normal information, and we also have the privilege information. So the input to output on input to normal component are the original features processed by L number of hidden layers, and each having N number of nodes. And each hidden layer receive the input as the output of the preceding layer and the original features. So the first hidden layer can be represented here in equation 16, that is H1 equal to G X W1. And higher layers can be represented as Hi equal to G, that is Hi minus 1 comma X and WR. So, and in the similar fashion, we also have the privilege information, that is right-hand side privilege information. It is also generated by L-layer architecture where we input the original features. However, here privilege info component of the given architecture use separate set of weights that and biases both, that is W tilde I, beta tilde I. And they are generated randomly and kept fixed, and different activation functions used in privilege component. So similar to normal part, we fix the rectangular component with the n number of hidden nodes in each hidden layer of L layer architecture. So here each privilege hidden layer receive the input as the output of the previous privilege layer and the original features. So essentially we can write the output of the first hidden layer, that is H tilde 1 equal to Fx W tilde 1. And then for higher level in the same manner. And when we concatenate and we can find out the solution, then we can optimize it. Okay. So now further, we have implemented these algorithm, this deep RVFL plus and EDRVFL plus. We focused on Alzheimer disease. So in here, we can see that we have considered RVFL variants, and we also have deep RVFL, EDRVFL, and the last three last one are proposed by us, that is deep RVFL plus and EDRVFL plus here in this plot. using this privilege information. And we can see that first case is CN versus AD, means control normal with Alzheimer disease. So this is the uh, simplest case because we have the two images, a healthy person and we have the Alzheimer disease patients. So two images, so it's easy to distinguish. So as I have shown the Alzheimer brain and healthy brain. So it's highly complex and completely different images. So easy to access and easy to visualize and easy to classify. So, and we have used different activation concepts and we can see their performance. And we also have another case, control normal with MCI, that is mild cognitive impairment. So this is the case just before Alzheimer disease. So here we also have done exactly on the similar case. And we have highly complex one, that is MCI versus AD. MCI is just before AD. So to distinguish two MRI images is really very difficult. So if we are getting the better accuracy, that's really great. So we can see that the performance of our model is promising, and it can give our future way to detect Alzheimer disease, or we can classify at the early stage. So now I'm moving further to discuss another variant, graph embedded ensemble deep RVFL. So we can use here essentially the graph embedded approach in RVFL network. And we further also have discussed its deep variants, ensemble deep variants. So, and this one we usually called shallow model, shallow EGERVFL. It has a single hidden layer and it has less capability to capture complex hidden relationship within the data set. So to overcome that issue, we also have extended our concept for the ensemble deep variant. And we propose this one. More details are available here. So we can see here that the standard RVFL model does not consider the geometric aspect of the data while optimizing the output parameters, and hence it has a lower generalization performance. And the optimization problem of the extended graph embedded RVFL model, it can be defined with this equation 20. So here the first term, it represents the empirical error, and the second term represent the graph regularization term, and the last term, it represent the regularization term, and both the regularization parameter, that is eta and this delta, it handle the impact of these two regularization terms. So now, and finally, when we solve these problems and we can get the beta, that is output matrix. So after calculating this beta, that is H transpose H plus lambda S plus eta I inverse H transpose Y. So this output of the graph embedded model for a new samples is taken similar to standard RVFL model. So now in graph embedding framework, there is an undirected weighted graph, that is G, where X and sigma are input data and similarity matrix respectively. And each element in the matrix sigma represent the relationship between two graph vertices xi. Moreover, we have another penalty graph GP. Here, each element of the weight matrix represent the penalty weights that are given to the specific relationship between the graph vertices in X, and the optimization problem of the graph embedding, it can be defined in equation 22, that is W star. So we can see that we have W star is arc min summation norm of W naught transpose Xi minus W naught transpose Xj square sigma Ij. And then we can rewrite this in this manner. And then we explain the meaning of it, that is transpose. This TR is a trace operator, and W0 is a transformation matrix, and L is the graph Laplacian matrix, and L is the intrinsic graph G, and D is the diagonal matrix, where each diagonal element DI can be represented like this. So typically, either V is a diagonal matrix for a scale normalization, or it is the Laplacian matrix of penalty graph GP, and V is equal to LP. LP is dP minus sigma P, and Q is a constant. And the solution can be obtained by solving this problem 23, where the meaning of SI is a matrix X transpose LX and SP is X transpose BX. It means that eigenvectors of these matrix S, it form the transformation matrix, and this matrix S, it consider both intrinsic and penalty graph relationship within the data. Okay, now to move ahead, so we can see that we have this flow chart of this eigenvalue, this EGER-VFL, especially for Alzheimer disease. So what we have done, that we have the original feature space, and then we extend this feature space, and then we do randomized feature space and concatenated feature space both. And then we calculate the matrix S, then we train this, and finally we get the output. So now, if we look at the numerical experiments on CN versus Alzheimer disease case, so we have again considered different activation functions, and we have taken RVFL, ADRVFL, and deep RVFL, both three. And the last four columns are proposed by us, and we can see that the performance is promising, especially for CN versus AD here in most of the cases. And here also we can say CN versus MCI. So we also see that, for example, cell activation functions. So we have in the baseline, we have up to maximum 61%. But if we look at our idea, our approach, it is going up to 65%. So it's huge, significant difference. So in this way, we can see that even for this one, another one also, ReLU functions, sigmoid functions. So a big difference. So we have highlighted bold one, the top two models. In most of the time, except one or two cases, our one of the approaches performing very well. And this is the difficult case, MCI versus ED case. MCI versus ED case means MCI, mild cognitive impairment, just before Alzheimer disease. So to classify this data is really very difficult. So now, even though we can see that by taking different activation functions, so we can observe that our last four columns, the performance is really promising, except one or two cases. So in general, we can say that this idea using graph embedded approach and its ensemble deep approach performs very well. This is we can conclude. And to move ahead, we also have done some experiments on UCI and key data sets. Since our work was focused on Alzheimer disease data sets, but we also have added uh, benchmark data, some UCI and key data set just to show the efficiency of the proposed approach. So here also we can see that in the last four columns, so we can, I think other than first three columns, so we have the rest from our side. So we can see that some of them are performing very well. So now this is the future trends of Alzheimer disease. So if you are really interested to work on this direction, so there are a lot of scope. So we can see that we have some deep learning architectures used in bridge estimation, including feed-forward neural network, convolution neural network, VGGNet, ResNet, and ensemble of deep learning models. So such architectures and applications under focused. So there are a lot of scope, especially for Alzheimer disease, how to see the brain age with cognitive decline and integration of multimodality, identify the biomarkers and uncertainty estimations, and developing deep learning algorithms or ensemble deep learning algorithm. And this is another specific information I have shown in the last lecture, that this is our recent approach, that we have written a comprehensive review on deep learning for brain age estimation. So since we have not added Ensemble Deep, the reason is there are only a few papers on Ensemble Deep. So we have focused on deep learning for brain age estimation. So, and from this review, we observe that a lot of scope are available for researcher, for clinical people to help the society. So even if we look at, since people are working on deep learning, so explainability is one of the major issue. So especially for doctors. So explainable, if we use the explainable AI, it will really help and understand the relationship uh, for the practical applications of the model. So it will clearly explain the more information about the data. So now, and we also have developing a new deep learning architectures. So like deep learning, ensemble deep learning. So it can help for improve the performance or improve the predictions. So the idea is for the early detections, early predictions of Alzheimer disease. So this is a big challenge, as I explained in first or second slide, that in 2018 report, 50 million people are affected with Alzheimer disease. So, and it is going to be triple. So a neurological disorder disease is really a big challenge in India. Either we go for Alzheimer disease or Parkinson or schizophrenia, or we go for brain age. So these neurological disorder disease is really a big challenge for researchers as well as clinical people to work on together and come up with a better solution with less cost. So it will help the society. As we see that the brain age difference with cognitive decline is really a general problem when the age is moving after 60 or 65. So we can see that the brain ages decline as the age is more. And we had to see the brain age affected due to Alzheimer, Parkinson, or other neural disorder disease. And we also have to work another possible direction, that's significant brain region extraction. So if we are able to identify a specific brain region related to age gap, so that will also really help us to understand and to work further. So it is study the effect of the age group and gender on the regions affecting the brain age. And also another direction, that integration of multimodal data, that is the brain age difference also depends on other factors like iron deposition, brain connectivity, and metabolic variations, and the combination with other modality. That's why we mentioned multimodal data, combination with other multimodal that can provide new biomarkers. And also we have another direction, adversarial perturbation and uncertainty estimation. So to develop a robust and safe deep learning networks for adversarial perturbation, and more focus on uncertainty estimation for deep learning. So more information about this work is available. It already published recently in Information Fusion Elsewhere journal. So if you are interested more, so please go through that paper. So it will really help more on this idea. So we also have focused on deep learning for Alzheimer disease. So it is also published recently in IEEE transactions on computational and degenerative, some IEEE TCDS journal. It's IEEE CIS journal. So you can see that review. So the name, I think this is deep learning for Alzheimer disease, a diagnosis, a review. So please see that also. And we also, my group also have written another work, similar work, that is uh, machine learning for Alzheimer disease, a review. So please go through these review papers if you are really interested to work on either machine learning or deep learning for Alzheimer disease. So, and if you are interested to go for Ensemble deep learning for Alzheimer disease, or Ensemble deep learning for other Parkinson disease or schizophrenia, so my recommendation is to please read the literature. And the first literature I already discussed today, called Ensemble deep learning, a review. So it is available online in journal Engineering Applications of Alzheimer Disease, elsewhere, Engineering Application of Artificial Intelligence. So this is elsewhere journal. So please see this paper if you are focusing or if you are interested to work on Ensemble deep learning for Alzheimer disease. So now I think I can take a few questions from the audience. And this is now I'm repeating the slide that we have one special issue, and which is very close to us deadline, that is only 2 months are left. So if you are working on advances in fuzzy deep learning for biomedical data, so you're welcome to. So I'm almost done from my part. So I was essentially discussing another recent work, uh, deep learning based diagnosis and prognosis of Alzheimer disease. It's also a review paper. It was published recently in 2023 in IEEE transactions on cognitive and development system. So essentially what we have done here, we have briefly introduced and clinical equivalent neuroimaging model diagnosis. Please check your mic. I think some issue from your side in the audio.
Yes, I got it rectified.
Okay. So to move ahead, we also have discussed in this review that we also have discussed the available data sets for deep learning for Alzheimer's disease that have been used by the researchers. And we also have discussed several deep learning algorithms that have been used for Alzheimer's disease diagnosis. And we also have discussed the advantages and limitations of various deep learning algorithms for Alzheimer's disease detections and predictions. And future scope also have been discussed that have been given the recommendation from other researchers and with our recommendations that can be helpful for developing a deep learning algorithm for Alzheimer's disease. So I think I can stop here my lecture. So I was just mentioning that this is a repetitive slide just to advertise my special issue on advances in fuzzy deep learning for biomedical data. So in IEEE transactions and fuzzy systems, if any of you are interested and have the relevant work, high quality work, please submit. So with this, thank you so much for your attention. And I'm extremely thankful to the organizer, especially Professor Sriparna Saha, for giving me this opportunity to deliver this talk.